Conference ideas. So does anyone have ideas of what they want to talk about this afternoon? I know we'll continue the dynamical star formation. Other ideas people want to talk about? Is it too early?
Okay,
yeah.
Just whether or not cores exist.
Oh, do cores exist? Okay.
It was Henry's idea, so.
That was Kara. Just encouraged her.
Okay.
Oh.
Sorry?
That again.
How about?
Do clumps exist?
Sorry?
Do clumps exist? No.
Like, what is the core? That's very deep. You get very philosophical. What about, so like, given that the conference theme is linking observation and simulations, do you guys want something on that? Like, how should we get observers and theorists in a room together to talk?
Statistical intercomparisons for observations and simulations.
Sorry?
Supposed to say that
You guys say it louder though.
simulations.
So, statistical comparison. Sorry, what was the rest of it? Statistical
It's in
comparison.
observations at simulations.
So, I would say we should begin, but at the end of the session, we'll come back to this when people are a bit more awake and put up some more ideas.
I don't know. I don't answer that. Please don't answer that. Please be aware.
Yeah. Yeah, because the other is, and so put it on the vote for dinner. Yeah. I just wanted to let you know in case you hadn't communicating. Okay, or call.
So, I think we're gonna start. So, good morning, everyone. So, the first speaker will be Michael Kufmeyer, and he's going to talk about the title of the talk is towards demystifying the role of magnetic field in star formation.
Yes, thank you very much. Okay, yeah, thank you for. Can you hear me? Yeah. Thank you for having me here. So, what I'm going to talk about is, in parts, talking about this wonderful structure here, which is part of a much bigger complex of a much larger giant molecular cloud, and this is part of zoom-in simulations that I've been carrying out for quite some time now, and that's what I'm going to talk about. So, when you think about star formation, so it's important to realize, as we all know here, that stars are born in large assemblies of gas, and stars form in different environments provided by the giant molecular clouds. Well, we all know this, that's why we are here, we're talking a lot about it, and nevertheless it's important to emphasize, because from a modeler's point of view, quite often I think we don't appreciate this enough, that these are observations. This is a sketch by Leguec for Serpent's SMM1. This recent paper came out last week, and what you see is this is part of you see like different cores, different protostars forming. You see these filamentary structures, and it's quite messed up compared to a picture where a single star forms from a single core. So what you typically do when you do formation simulations of a single protostar. And so in order to actually account for this turbulent structure for the giant molecular cloud, we're looking for an alternative approach. So we're doing zoom-in simulations, and we'll quickly remind you what we are doing, what we're doing here is, so we start with a giant molecular cloud, here 40 parsec in scale. This has like a filamentary structure. We model the stars in our model with zinc particles. The turbulence in our box is a result of supernova feedback. The code we've been using for this is a Ramses code, or it's a modified version of Ramses. Important to always remember that the reason why we can carry out these simulations is because of Larson's relations, so we can kind of say larger spatial scales evolve on larger time scales. And as I said, the box size is 40 parsec cube. We use adaptive mesh refinement, and we solve the equations for ideal MHD. In more concrete, the zoom-in step, so we have this filamentary box, we have this giant snapshot of the giant molecular cloud, which we then evolve for 4 to 5 million years with maximum resolution of level of refinement 16. What does it mean? That means if you have a box size of 40 parsec, then you have a minimum cell size of 40 parsec times 2 to the power of minus 16, and that corresponds then to 126 AU. During this evolution, we form a number of different stars, or hundreds of stars with different mass, different zinc particles. And then the actual zoom-in step, we pick a star that is like evolved to 1 or 2 solar masses, and we rerun the simulation with higher resolution in the region where the star forms. But keep in mind that we still have the entire box, so we don't excise anything. We still keep the entire box. We just resolve the surrounding with low resolution, and then we do that for about.
Clarifying question.
Yes.
You said we rerun the simulation. Do you actually mean that you start over from zero?
No. So what you do is we evolve this for 4 or 5 million years with a cadence of 50,000 years at that resolution. And then you take the snapshot.
Start from there.
Yeah.
Start from the snapshot, right?
Yeah.
On the small scale.
Exactly. So you start from a snapshot before, like a few 10,000 years before the sink has formed. And you have to do that because you want to form the sink at higher resolution to get the collapse right. And so that's what I mean when I say rerun. We don't start back from
Don't
scratch.
say that.
Yeah.
Native English speakers will be confused.
Okay. So what should I say?
That means you start over.
Okay.
Rerun means you start over. So run. Just say run.
Okay. Thanks.
Run. Go ahead. That's why I was confused.
Oh, years of mistakes, yeah. So then we run another simulation. In principle, we can also run another simulation where we zoom in on the earliest phase, and based on the zoom in, so it's kind of a zoom in of a zoom in, and this is like resolution-wise the highest what we've been doing. So the box now is only like 7.5 AU, and what you see is the density here. The field lines correspond to the magnetic field, and you can somewhat see the arrows, so you can actually zoom in onto such an outflow at the earliest phase of star formation here, and that's quite nice because you still have have it in the context of larger surroundings, of the larger environment. Okay. Another thing I want to mention here is we have different things, they form in different environments. And an important result there is that when we zoom in onto the disk scale, so this to the left, these are results of the simulations, 50,000 years after the formation of the sink, and you can see a diversity there in disks. So in some cases you form rather large disks, in other cases you basically don't form any disk because of significant magnetic braking. And what I think is important to emphasize here as well are these filamentary arms that you see here, also on the smaller scales, kind of, I can call it streamer, we call them accretion channel or so. And I was quite stunned when I saw this summer there was a paper by Yen et al., observations of H0 plus in HL tau, where they actually see also such a spiral arm or filamentary arm in the gas. So these structures might actually be more occurrent than you would think of from dust observations. All right. Disclaimer here. So typical arguments then you may remember that these are ideal MHD simulations, and typical argument is then, well, how can you form disk? You overestimate magnetic braking. This is what you solve. You should solve this. You should solve non-ideal MHD equations and account for all these effects. And my answer is yes, certainly this is important, especially if you want to have the structure in the disk right and the detailed process. Because non-ideal MHD effects, they enhance the formation of disks, they cause thinner disks, and they also suppress like a so-called magnetic interchange instability. But be also aware that you have to account also for the turbulence that is in the giant molecular cloud. We have different ionization rates, so depending on the ionization rate, the importance of the non-ideal MHD effects may vary. And so the resistivities they are not truly constant, so that's kind of the point relating to the ionization rate. So it's not just a simple picture. And to illustrate this here, so to the left you see these are results from core collapse simulations by Masson et al. You see the x-axis, you see the density. On the y-axis you see the B field. And you see if you look at the red colors, these are results from ideal MHD simulations, and blue color is non-ideal MHD. And what you see is there's an order of magnitude difference in magnetic field strength compared to between non-ideal MHD and ideal MHD. You have this plateau value if you account for ambipolar diffusion. However, if we do look at into our simulations, we can see this. Certainly, this is an effect. So because of flux freezing, the core collapses, the magnetic field is dragged in towards the center, and yes, the magnetic field is probably too strong, but you can see it's not as severe as you would naively think from the simplified picture. So nevertheless, once again, to point out, it really depends what you're looking at, what the scales you're looking at. If you really wanted to have like a detailed model of a disk where you want to resolve like AU scales, you need to account for the non-ideal MHD effects, but for the formation process, in the larger context, it's probably not as important. Okay. Back to the diversity, because that's an important part as well. So these are 9 different, call it pre-stellar cores. So the size here is 50. Each patch is 50,000 AU square, and you can see differences in the environment. Some cases are more isolated, others are much more perturbed, and let's take a closer look at to this object here, into the collapse phase at higher resolution. Let's zoom in. This is already after the formation of the primary. In the center, you can see there's a star with a small disk, and this is about 40,000 years after the formation of the central star. And now we evolve the simulation. You can see what we see is like to the upper left, there's a first companion forming, and now to the lower right, we see a second companion forming. They're approaching each other. So we have this formation of a multiple system. And what is striking when you look at this, when we looked into this region, so it was actually just by chance we zoomed in, and then we noticed these structures here occurring as for like 10 to 20,000 years. These connecting structures between two of the stars. And well, I think this was quite interesting because at the time I saw this. Then there was a lot of debate, a lot of discussion about the bridge in iOS 16.29.3, and then I thought like, okay, it's also the white color scheme. So then I thought like, wait, this looks actually somewhat similar. So it's indicative that these bridge structures might actually be a transient phenomenon because of the turbulent motion in the giant molecular cloud. If we look at the kinematics here, so what you see on the right hand side, you see the velocity along the line of sight, and what you can see is actually that these bridges are rather kinematically quiescent, but note that it's only quiescent along the line of sight. So actually, if we look in the plane, there are actually some motions towards one of the protostars. So nevertheless, because it's basically a projection effect, that it appears kinematically quiescent. Okay, what about magnetic fields? Well, unfortunately, I couldn't make the movie one here, but I hope you can see it here, so to get a handle on it, get an idea of it. Anyways, so what you see is you see this bridge structure here in 3D, and the magnetic field lines here, and you can see it's like they are somewhat perturbed. I visualized the strongest field lines, and they are associated with the primary, and you can somewhat see a mild outflow in this structure. Well, what I said before, these bridge structures, apparently they're like a transient phenomenon, and there might actually be then this way a tracer of turbulent fragmentation. And at least what the simulation suggests here, that the magnetic field actually for this formation of these elongated structures, they are not as important. So it's really more, they don't really care so much about it because there's not a strong correlation with in the bridge and the magnetic field here. Well, this is maybe a little bit at odds with observations. So these are results from Satterway et al. And I think Ian was also involved in this. So you see, there's quite a sample now of dust polarization on these scales, and there it seems to be that there is actually a correlation here with the bridge and the magnetic field lines. But so what would be very interesting, of course, is this, like, to do synthetic observations based on the simulations, and to look at the dust features. And so here, this is work in progress that I'm currently doing with Stefan Reisler in Heidelberg. And Stefan will talk much more about it tomorrow, I guess. So you can see here that Stokes' eye and the arrows, or like these lines here, they correspond to the dust polarization vectors. You can somewhat see a mild difference here in the bridge structure there of the vectors, but it's not like it's complicated. It's not as easy. So yeah, stay tuned and listen to what Stefan has to say tomorrow. And with that, I want to conclude my talk. So the main points is really to emphasize can't be emphasized enough in the overall context. So keep in mind that protostellar environments are diverse, and so also the formation path of stars. Even though you have a star ending with the same life, with the same mass, might actually have a different accretion history. And these streamers and bridge-like structures, they seem to be a natural byproduct of embedded star formation. And yeah, in the future, this is sort of work in progress. What we need is synthetic observations to link the observational data with the simulations. Thank you very much.
So thank you, Michael, for this nice presentation. Are there any questions?
Me or Annalisa? You start, Annalisa.
Can you tell us what are the rules for making the sync particles? And then the other question is, what happens when you run without ideal MHD at all?
So the last question, I don't know, because it's so this is a very heavy simulation. So we only ran it with the magnetic fields. So I can somewhat guess. Sorry.
Can you speculate about the importance?
Yeah, sure. So what you would expect is that the disks, I would expect to see larger disks. So you would also I would expect less launching of outflow motions. And I would expect that because what we see, this is the case in our scenario, we have like a very strong magnetic field in the disk. So you would expect that there's a little, that the disks are probably getting a little bit thinner there in that case. But with non-ideal, so it would be something with non-ideal MHD that you would circumvent as well. To the sync particles, so we form a sync particle when it's gravitationally unstable. So when you have like when you resolve it, I think we use. Not completely sure which number we use, but I think it's like 32 cells above the gene length, and then you trigger sync formation, and then you accrete from the surroundings with the gradient, and we can talk about it in the break.
Just one more question, and if Caroline.
So your difference that you do not see a strong association of magnetic fields with the streamers, whereas in 16293 one sees this. Could the simple reason be that you may have too low magnetic fields in your simulations, that this is just that are not as strong?
I don't think so, because in generally we don't have any dissipation of the magnetic field, so it's ideal MHD. So with this case already, and we, well, sure, it could be that region.
A bit higher magnetic fields.
So,
but we actually saw the opposite, that the flow tracks the magnetic field.
yeah, okay. So. In what's
So because I mean the structure of the magnetic field is
yeah, I can see. I mean I think it seems to be like if you look at the synthetic observations, there seems to be some deviation from it, which is apparently associated with the flow in this bridge structure. So that would be consistent, but it's not fully.
speculation we had in the paper.
But
Maybe one last quick question.
sure.
Just to answer Henrik a little bit, a couple of years ago, there was some beautiful ALMA data from Chad Hull about serpents, this first region that you showed. And then Blake Sikorkart and Philip Mokes ran a bunch of the repo simulations, and they did vary the magnetic field a lot.
It's true.
You do see very different alignments of these kind of streamer-like features. There's a plot at the end of that paper that answers.
Can I say like one last sentence? Is also so. This is one sample. This is one zoom-in region. So what would be not required is like, to have a statistical handle how it would look like in a different region. Then it might be different. Yeah.
Okay, I think we need to stop here and we continue discussion. So now we are going to hear Caroline Geiser, sorry. He's going to talk about the feature complexity in high mass platform regions.
Okay. Can you hear me? Great. Good morning. I'm Caroline. I'm a PhD student at MPIA working in Henrik Beuter's star formation group. And in this talk, I will give you an overview how we study the chemical composition of the molecular gas in high mass star forming regions, based on observations of the core project and applying the physical chemical model muscle. Just as a quick introduction of the core project, this is a NOEMA large program of 18 high mass star forming regions that were observed down to an angular resolution of about 0.3 to 0.4 arc seconds at 1 millimeter, and we also have 2 pilot regions observed with the same setup. With the Widex correlator at intermediate spectral resolution, we have a 4 gigahertz broad spectral window where we can study many molecular lines. And in order to account for missing flux due to missing short spacings, all of these regions were also observed with the IRAM 30-meter telescope. And in the past 2 years, we already published lots of results. So with this data set, one can study lots of different things. One can study the fragmentation, the kinematics, outflows, but also the chemical properties. And this is an overview of the sample. So this is the 1 millimeter continuum. The x and y axes are already in linear scales, so accounted for distance. And the surprising result was that even though they were selected as a kind of homogeneous sample, if you look at this high angular resolution, basically each region looks different from another. And some of these regions are rather isolated, single cores, while others fragment into multiple subcores. There are some regions which are more spherically symmetric, while we also have lots of filamentary-like structures. And this can be, for example, explained by varying density structures or different magnetic field strength in these regions. But for that, we need more observations, which we will get in the near future. Now, to study the chemical content, we started with a case study of the AFGL 2591 region. You can see here on the left a sketch of that region in color. That's how it looks like in the infrared in K-band. And you see this bright blob and this huge outflow lobe to the west. And on top of that, in green contours, that's centimeter emission, where a little cluster is revealed. But the powering source in this region is that VLA3 hot core here. And the dashed line here shows our Noema primary beam, but what we really only detect is the VLA3 hot core here. So in order to really dig into the chemistry, we first had a look at the physical structure. So we had a look at the temperature and density of that hot core, which is shown here on the right. So first here in contours, that's the 1 millimeter continuum. And we thought that this is kind of one of the simple regions because it looks rather spherically symmetric. There's no further fragmentation. But as you've seen yesterday in Sue's talk, if we go to a higher angular resolution, then it also starts fragmenting again. So if you want to talk, you can talk with Sue about these higher angular resolution data. We just assume in this study that it's one hot core. We use formaldehyde and methyl cyanide lines to determine the temperature in the region. For that, we fit the lines with the X-Class software. And with X-Class, you can create these temperature maps. And formaldehyde is rather tracing the extended low-temperature gas up to around 100 Kelvin. Here in the central part, the lines get optically thick, so it's not possible anymore to determine the temperature. But luckily for that, we have methyl cyanide that really traces the densest inner region up to about 200 Kelvin. And by combining these temperature maps and assuming spherical symmetry, we can determine the temperature power law index, which is in this case 0.4, which is in perfect agreement with theoretical predictions. We also used the continuum visibilities to infer the density power law index, where we get a value of about 0.7, and we needed that kind of as an input for our physical chemical model. Now, to quantify the chemical content, we first extracted the spectrum here towards the continuum peak position and fitted all molecules that we can detect. And this is shown here. So in red, we have our observations for all molecules. We infer the molecular hydrogen column density from the dust continuum, but everything else is then again fitted with X-class. And on top of that, we now wanted to test how well we understand the chemistry in this case. So we applied the physical chemical model MUSCLE, which stands for multi-stage chemical code, and it has the time-dependent gas crane chemical network alchemic developed by Dima Semenov, and the physical model consists of a static 1D physical structure where the temperature and density are described by power laws. And you give us an input, a parameter set of different physical structures, and then for each physical model, the chemical network runs up to 100,000 years. And then afterwards, the modeled and observed column densities are compared, and by a least chi-square analysis, one can determine the best fit chemical age, but then also the best fit chemical structure. And our results are shown here in blue. So that are our best fit model results. In total, we can explain 10 out of 14 molecules within the uncertainties. And the best fit chemical age is also consistent with previous studies of this hot core, where we get about 20,000 years. It was quite surprising that the model works so well, because it's a really simplistic model. But if we have a look at the distribution of the molecular gas from our observations at really high angular resolution, we see that this assumption of 1D symmetry is not valid anymore, which is shown here on the right. So on top you have the line integrated intensity of methanol from the observations, and on the bottom the line integrated intensity from methyl cyanide. And while it kind of would work for methyl cyanide to assume spherical symmetry, it definitely breaks down here for methanol, where we have these ring-like structures. So what we want to do is improve our physical-chemical model, but what you've heard yesterday is that it's really complicated to have like a complex physical structure and run on top of that also the chemistry, but we are working on that. But I mean, we all know there are many hot cores which have a high molecular composition, but with this data set, we want to go now one step further and really look at this sample, which were all observed within the same setup, to see how the chemistry varies from region to region. And for that, we extract 140 spectra out of the 20 regions and fit all lines that we can detect with X-class. Here's just another continuum image of IRAS 21078 as an example. And here are some positions where we pick out the spectra. So of course we look at the kind of core positions where we have these high flux density, but we also kind of look at the envelope, so where we don't detect much in the continuum. Here's just a list of what we detect in all the regions. We have CO isotopologues, we have a lot of sulfur-bearing species, but then we also have a lot of complex organic molecules within this 4 gigahertz broad spectral window. Now you may wonder, okay, do all spectra look the same? Do they all have the same emission lines detected? Of course not, that would be too simple. So on the left you can see the spectrum of AFGL 2591, and on top of that the X-class fit, and you can see that this is a typical hot core. We have many emission lines. And on the right side, another region, S87 IRAS1, where we basically only detect CO isotopologues and a bit of SO and a tiny bit of formaldehyde. So we have line poor and line rich regions. And the question now is, why is this the case? Is this because of different evolutionary stages? And what is the effect of the environment on these regions? Another thing that we're currently working on is, because we have so many molecules, we can really look at how do they correlate with each other. And this is just one example. So here is plotted the torsionally excited methanol against the ground state methanol, normalized to the C18O column density. And if you ignore this point, you can see a nice correlation. And if we put on top of that the kinetic temperature, you can also see that the more we have, the higher is also the temperature. So we can really, with these data, do lots of statistics and correlations. So to summarize, we look at 20 high mass star forming regions and study the chemical composition. we infer the temperature and column density using the X-class software, and we then apply or want to apply the physical chemical modeling with muscle. And we see line-poor and line-rich regions, so we really want to understand, is this a reason because of the different evolutionary stages, or is this because of the environment? And as we already heard, we use molecules to trace things, so we should understand the differences that we observe. So what we need to do is really combine kind of physical properties of the regions, for example, the temperature, the density, and in the future we will also get information about the magnetic fields, combine that with the chemical composition, and also have a look at the evolutionary stage to try to understand why we see so much variety in the spectra, and we are currently working on that. So thank you very much for your attention.
So maybe before the question, if the next speaker can come line up here for the introductory talk, please. And there is no question?
Yeah, you reported a chemical age of around 20,000 years for the static model. Can you say something about how fast the envelope or the core gas is evolving dynamically, either from the free fall time or the crossing time? To answer the question, is the chemistry changing faster than the gas dynamics, or the reverse?
I think it depends really on the molecules. So there are molecules which react very fast and others have longer time scales. What I didn't mention in this talk, so this hot core stage is kind of preceded by an IRDC stage where we have kind of a constant density. And we really need that to really form first the molecules on the grains at low temperatures, and then we kind of have these step-like functions where we increase the temperature. So it's not static like the whole 20,000 years. And that is important, that you don't have really one temperature at these high temperatures, because then you wouldn't form all these complex organic molecules, because it would just be too hot. So we really need this warm-up stage, and that's why we want to improve this model to have kind of a smooth transition, include more physics kind of in the warm-up, so that we can explain more molecules.
How long does the warm-up stage last?
Sorry?
How long does the warm-up stage last?
I mean, that depends on which mass your protostar has. I mean, or do you mean like for this hot core?
Well, yeah, the results that you're quoting.
Yeah. So we have this IRDC stage which goes for 15,000 years. And then we have 5,000 years of our hot core phase.
Okay, thank you.
Can you go back one slide?
Yes.
So I'm just curious about this outlier.
Yeah.
So can you tell me things about measurement?
Yes.
Do you think there's something different about that?
Yes, so the fitting is basically just assuming we have one emission component, and if you look at the spectra, some of the regions have multiple components along the line of sight, so it doesn't really work to fit this with one emission component, and yeah, I think that's just...
the only one that has line of sight conclusion, or is it...
No, there are multiples, and I'm currently working on kind of post-processing the fitting and to exclude kind of these outliers.
Okay, so I think we should thank Caroline again. Oh yes. So now we will have some introductory talk, and so each talk will be 2 minutes sharp, and we're going to start with Jonas Ayat.
Okay, so good morning, everyone. My name is Jonas Ayat, and I'm a first-year PhD student at MPIA. and I'm mainly working on the H1 data of the Thor survey. And what I'm in particular interested in is, on the one hand, H1 self-absorption. So just basically to isolate and separate the cold atomic gas from the warmer component. And what you can see here in this upper panel on the left-hand side is the integrated emission of H1 towards one particular giant molecular filament of the Reagan 2014 paper. And I think it's designated bone 5, is it? Also within these, well, along a subsection of this giant molecular filament. So this is a rather interesting region. And what you can see here in emission is basically both warm and cold atomic gas. So one way to separate these two components, to disentangle these components, is through studying H1 self-absorption. And if we look at one spectrum, one example spectrum, also towards like one region within these black contours, which are 13CO contours, one way to extract these HESA features is by looking at 13CO emission peaks, which you can see here in the blue spectrum. And once we've done that, we can extract these HESA features by fitting simple polynomial functions to the baselines of these emission spectra. And then we can infer the kinematics and mass of this cold atomic gas. So this is rather interesting. I've also made a poster about this, so please come check it out. And on the other hand, we can also, if we move to negative VLSR velocities, so we don't have this line of sight confusion, we can actually see also very nice filamentary structures in H1 emission. So I just wanted to bring it up since we have a lot of experts here on filaments and bones and spurs of the Milky Way. So we haven't done much analysis of this, but please come talk to me and I'll be happy to discuss it with you. Thank you.
Good morning, everyone. My name is Joanne Juan. I'm a postdoc also working at MPIA at the Thor project. As Jonas already gave you a nice introduction of some of the case study, here I would like to show you an overview of the H1 and the continuum. Oh, holy, 1 second. Yeah, it's much better. So you see on the top you have the H1 channel map movie, and on the bottom you have the continuum. As the channel moves, you see all these complex H1 emission structures. While in the continuum, I marked some of the very famous H2 continuum sources. You can also see some of those absorption structures there. And go back to the slides. Just a second. And okay, here we go. And the same on the left side, you see the channel map. Now it's easier to see because they don't move. And with this H1 emission, we can play a little bit. And on the top right side, I construct this face-on view of the average surface density of H1 as it overplot with the spiral arm model from Mark Reed's paper. You can see that some of the emission agrees very well. Oh, again, also I'm not sure it's clear enough. The crosses here is the H2 regions from Lawrence Anderson's paper. And you can see that some of the H2 regions and also some of the emission, they agreed relatively well. And then also some of the H1 emission also follows the spiral arms structure relatively well, as you can see, especially like the Sagittarius arm. On the other hand, we can also play with the PV diagram if I average the emission along the latitude range. And here I overplot something very interesting. Is the PV the ratio map of the H1 and 13CO. As you can already see that follow the arms, you have very low ratios where there's strong 13CO emission, but where there is no 13CO emission, the ratio is high. It shows there's like a very strong atomic to molecular gas ratio, in arm and inter arm. Feel free to come to my poster.
So now we are going to hear Ricardo Franceschi.
Yeah.
everyone. I'm Ricardo Franceschi and just started my PhD at the MPA working with Thomas. And the purpose of my research will be to try to constrain the fundamental parameters of planet-forming disks. And this is very important for many reasons, but in particular, I'm interested in the connection between the disk physics and chemistry and the huge variety of properties that we observe in exoplanet population. And for instance, if we take the total mass of the disk, is the key parameter of the mass and frequency that we observe in exoplanet distribution. And the turbulent viscosity is what determines the transport of mass and angular momentum in the disk, and other properties such as grain growth and dust mixing. So if you remember for yesterday, the recap about the unconference about the disk mass estimates, we already know more or less what we'll be focused on right now. As a matter of fact, I'm studying these different approaches to determine the mass of the disk, such as the observation or multi-wavelength observation of the dust line location, or the observation in the near infrared of the dust scattering surface that gives you the pressure scale height of the disk. And we can also use molecular tracers, such as HD and CO isotope logs. And each one of these techniques is based on different physical processes that take place into the disk environment. So a different understanding of the process that present in the disk are required. So if you have an interest in this kind of topic or just any kind of comments, please come to find me.
And so now we're going to hear Melanie Schmidt.
Okay, good morning, everybody. My name is Melanie Schmidt. I'm a postdoc at Heidelberg University, and I'm interested in the cycle of matter in galaxies. So, contrary to what we observe on large scale in galaxies, where galaxies follow a star formation relation, so gas surface density correlates very well with star formation rate surface density. When we zoom in and look at small scale, cloud scale in galaxy, what you see is a spatial decorrelation, as here, between the gas in blue and young stellar regions in red. So we have developed a new statistical method based on a multi-scale approach to characterize the spatial decorrelation and measure from that the evolutionary cycle of molecular clouds from their formation to collapse, star formation, and their destruction by feedback. We have applied this method to 9 galaxies of the Funk survey, and you can see the timeline of molecular clouds here. And the conclusion of these studies is that we observe short molecular cloud lifetimes, so from 1 to 3 dynamical times, with a long inert phase where CO is not associated with any H-alpha emission. We also measure short feedback phase, so clouds are destroyed within 1 to 5 megayears after the onset of massive star formation due to photoionization and winds. If we look a bit more closely to this result and look at how the cloud lifetime varies as a function of galactocentric radius, we can distinguish 2 regimes. One regime at high gas surface density, where so above 8 solar masses per parsec squared, where GMC lifetime are being set by galactic dynamics, for example, epicyclic perturbations or shear, and a regime at low gas surface density, where GMC decouple from the galactic dynamics and their lifetime is set by internal processes such as the free fall or the crossing time. So if you're interested in that, please come and talk to me. I have a poster, and these results have recently appeared on, yesterday, I've appeared on AstroPH. Thank you.
Thank you, Melanie. So, and for the last one, we're going to hear at Thomas Henning.
So we had already a perfect introduction to what we did by Michael, but we used another code, the Flash code, and we had another interest, was actually to find out what the fragmentation criterion for filaments is. And we isolated filaments in this simulation, and it turned out that they fragment earlier than predicted by the normal mass line ratio. And I think the reason for that is that we have external pressure acting in these simulations, not just the isolated filaments. Then we did another heroic study by actually Jiamei Chiang. We wanted to know what the star formation capability of the giant molecular filaments is. So he identified 40,000 young stellar objects using UKIT's and the VVV survey. And what we found is that the relation between star formation rate and dense gas mass, which we found for the local clouds, Charlie is not here, but he would show that, I guess, extends actually to the giant molecular filaments quite nicely. I have seen here the question, do cores exist? So we did a study to look for segregation in the core distribution for nearby clouds, and actually found segregation except for Taurus. And if the cores already show segregation, then of course that should have an impact on the star formation distribution later on. I think that's a quite interesting area of research, and I think we should follow up that a little bit, because normally we're considering the young stellar object distribution, not so much the core distribution, but that's something we should do. Okay, that's it, what we did last year, apart from many other things.
Okay, so now we're going to hear Cara Battersby. Battersby? How do you pronounce it?
Battersby, but it doesn't matter.
Battersby, sorry. And so it's going to be a framing and a research talk on the topic of observing.
Stretch if you need a stretch, because it'll be a longer one. I'm just going to set this up first. Let's take a minute before. Okay, so here. Thank you. I think I'll just hold this. Hello, good morning. I have to admit, well, first of all, I want to thank the organizers for inviting me to give this talk. I'm very honored, but also terrified. So 2 reasons I'm scared. One of them is because there's so many amazing people in this audience who know a lot about the things I'm going to talk about. Trying to review all the scales of the multi-wavelength ISM is not something anyone could do in 15 minutes, plus 15 minutes for research. So hope you don't mind what I chose. I think some of the stuff that we had this morning, the smaller scales in the chemistry, was a good counterpart to what I'm going to talk about today, which is more the moderate scales of star formation. And the second reason, I was nervous. Does anyone remember what happened the last time I gave a talk at the Harvard Heidelberg star formation meeting? What happened, Alyssa? Yep, Donald Trump was elected president. So hopefully today will be a better day, a less somber day. Yes. The public impeachment hearings start today. It seems like a good milestone, right? In 10 minutes, perfect. All right. Okay, so I'm going to cover scales of star formation in the Milky Way with special love for the galactic center and many, 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 many things left out. So I really hope that the discussion will be a productive time for you to talk about your favorite things that I left out, or unconference sessions are another great opportunity as well. So I'd like to start by just putting the Milky Way in the context of galaxies in the local universe. This is courtesy of the FANGS team. And so in terms of star formation rate and stellar mass, is this a pointer? It is. In stellar mass, this is where our Milky Way sits. It's mostly in the middle, just kind of a middle, everyday sort of galaxy in the local scale. And we don't have a picture like this of our Milky Way, of course. This is M51 from the PAUSE survey. And I just like to point out the beautiful structure that you see on the large scales of a galaxy. This one probably has much better defined spiral arms than we do. But when you look at the CO versus the 8 micron versus the near UV, you can see the width of the spiral arms in these different tracers and the complexities of the structures that we're talking about. Okay, so zooming back into the Milky Way, I have sort of a fake projection of what this would look like. So this is obviously not our galaxy, right? We all know this. We're all on the same page. This is M51. But now we're projecting onto this. Say we were observing here in M51, looking through this whole big line of sight. This is sort of what we see in our own galaxy, a big mishmash of CO, all from those different areas along the same line of sight. And then if we zoom in on some of those regions, we can see this is a beautiful filamentary structure, giant molecular cloud in our galaxy. And then if we go even further in, we'll see something called cores within this. And then if you go, then we have, so these are sort of some of the scales that we're starting out with here. So about clouds are scales of greater than 3 parsecs. You call that 5, 10 parsecs. You choose a number. I'm not going to complain. It's sort of arbitrary. I'm just going with the Bergen into Faya numbers here. And then we have clumps are the sort of clumpy objects in between, size scales of about 0.3 to 3 parsecs or so. And these are embedded within these giant molecular clouds. And then cores are arguably defined in many ways. We're just going again with this Bergen into Faya reference here. Less than 100 solar masses, about less than 0.3 parsecs. But you could also argue that a core should just be a thing that's going to form a single star or star system. There's a lot of discussion about that. But these are the general size scales that we're dealing with in the ISM. And as you can see, some of the problems that we have are just definitional, because we're dealing with a turbulent hierarchy and there aren't clearly defined boundaries between objects. So this is just sort of a brief overview of some of the size scales. Something I'm not going to talk about are the smaller size scales objects, such as disks, and we saw beautiful simulations of a protostar at really small scales today. I'm not going to talk about that in this talk, but that would be the next size scale for star formation, if I were. So to say something about clouds overall, I wanted to go to the Galactic Ring Survey. And so here is a picture of the overall view of the Galactic Ring Survey. This is about 46 arcsecond resolution, 13CO 1 to 0. And you can sort of get an idea of the 3D positions of these clouds and plot them on a galactic structure map and look at the density of them as a function of galactic radius. I'm not going to talk too much about the GRS results now because they're getting to be outdated, which is exciting. That means progress is happening. And there's some exciting new work going on. So Manuel will hopefully talk about this in his talk later, his work with Gauss Pi to do a better job of identifying these clouds and doing analysis on that. And then Tom Rice also has a really nice paper looking at updated dendrogram structures in the DAME data, so looking at updated molecular cloud properties based on highly improved analysis techniques. And we all know why these analysis techniques matter, right? It's because we're dealing with a substructured hierarchical ISM, and how you draw boundaries around things does matter. And so these are some exciting new results. Okay. So I had a slide back in the day of alphabet soup, just trying to talk about a couple of the big surveys that were happening and sort of the pictures of all these big surveys. But then people kept doing new surveys, and I got really tired and didn't want to make all these new plots. And I was like, I'm going to spell out all these acronyms. But luckily for all of you, there's this wonderful website called milkyway3d.org that Alyssa and Catherine monitor and keep track of. And it has all these large-scale surveys. It has links to the data pages, information about the wavelength, and then continuum over spectral line. So here I'm just plotting a couple of the spectral line surveys that I'll be talking about in the next couple of minutes for your reference. But if you want to make your own, if you want to investigate what kind of galactic plane surveys have been done, this is a great place to start. So as we've gotten away from these very large scale, lower resolution surveys of the galactic plane, we've transitioned from just looking at the cloud scale properties and like this object here to looking at these clump scale properties, these little embedded objects here. So these structures are smaller, not surprisingly. We're looking at size scales of about 1 parsec, and they always tend to have this filamentary type structure here. Temperatures about 20 Kelvin on average, and this is from a paper from James Urquhart looking at the Atlas Gal sources, mass versus radius, and in the context of which ones are forming low mass stars, high mass stars, and then your very massive protoclusters up here. You can see that when we're looking at these large galactic plane surveys, we're looking at things that are more distant on average, and so that means that you're generally forming massive stars because you're seeing distant, brighter things. Okay, some fun updates to these plots lately. So this is from Rigby et al. 2019, using the CHIMPS data, which is a JCMT survey. And so this is, again, a mass radius plot and showing the Atlas Gal sources that you saw before in red, the GRS sources and how those fall here, and then CHIMP sources, which are in between on these color scales here. So this gives you a good sense of, you don't see distinct boundaries between these objects. You have just a hierarchical structure of material that is sort of defined as either a cloud or a clump. There's also some nice work from the CORES team from Colombo et al. 2018, looking at the size line width relationship for, this includes a lot of the surveys that I talked about, so GRS. We also have Galactic Center stuff. We have some work from Mark Heyer and Tom Rice's survey. And in the background is also shown nearby galaxies and where they fit on this size radius relationship plot. So generally like a big clump of things that you can separate between them if you choose. All right, so we're also interested in the evolution of clumps. I chose my work to show here, but there's many other works that talk about the evolution of clumps. And so if you look at just the temperature of all these clumps and the different star formation properties, you can see that there's a clear trend from being less evolved to being slightly more evolved and then more evolved as you go along this general evolutionary phase here. This could also be selection bias, but that's the general idea, is that you have something that's not star forming, it collapses, it forms stars, it starts to show some star formation signatures early on, like some jet signatures, and then eventually some embedded protostar signatures, and eventually an H2 region inside of that. Okay. So all of these maps can also be used to look at the overall structure of the galaxy. So I've plotted here from a couple of these different surveys what the top-down view of the galaxy looks like from these surveys. And you can see that, I don't know, what can we see from this? Do we have spiral arms? We probably do, right? But they're not super clearly defined. I mean, part of this is like these maps are hard to make. This one, I like the overdensity plot. It almost looks like you see some spiral structure there. But there's still a lot of work to be done in terms of uncovering the overall 3D structure of our galaxy, but we're making some good progress on that. Okay, I couldn't give this talk without talking a little bit about these filamentary structures that we've seen in the last 10 years or so. These are everywhere in the galaxy, and they're not just these tiny little filaments that you'd expect to fragment out of giant molecular clouds. You actually have giant filaments, and they go by many names: giant molecular filaments, bones, these Herschel-defined structures, and these minimum spanning tree-defined structures. And so a lot of groups, some listed here, have identified these structures in many different observational tracers. And Catherine has a nice paper from 2018 where she combines all of these together and looks at the overall physical properties and also the distribution in the galactic plane. So as a function of longitude and velocity here, you can see the DAME CO data in the background, the Reed spiral arm models here, and then all of the different filaments from the different surveys up on top of that. So I think I should ask Catherine what she thinks, but I mean, my impression of this is that this might help us to inform galactic structure eventually, but right now it's sort of a chicken and egg problem still, because we're still trying to figure out exactly where the galactic structure, the spiral structure is, and also how well these filaments may or may not trace that. And she has, I'll get to that in a second. So she has some new work that will shed some light on that. This wasn't even planned, Thomas. I was going to show this plot from Jiamei's paper on the star formation rates of Milky Way filaments. This was, again, I agree, a completely heroic work looking at the star formation rates of all these different structures, and then as a function of the dense gas in both directions here. And you can see where all of those structures fit there. So that's a really great paper to check out if you're interested in the star formation rates. So in terms of figuring out the meaning of these large-scale filaments, Catherine has a really great paper that came out this year where she does these simulations. And this is all I'm going to say about it, because I think she's going to give a talk about it later today. You're not going to talk about it? Oh, well, sorry. She's not going to talk about it, so you have to read the paper or talk to Catherine about it. Yeah, but so uncovering the origin of these large-scale filaments by comparing simulations and observations. All right. So we've started with sort of an alphabet soup of all these different surveys, and I'm going to declare the 2010s to be the golden age of these large-scale galactic plane surveys. How lucky are we that we get lost in an alphabet soup of so much data that we don't even know what to do with it? I'm going to consider ourselves pretty lucky. And I'm going to declare 2020s to be the decade of these high-resolution follow-up surveys. So two that I'm particularly excited about are the ALMA IMF large program and the ALMA GAL large program. And so both of these are ALMA large programs. So ALMA has decided that following up on these sources at high resolution and going from these clump scales down to the core scales and not just looking at one object, two objects, but really like statistically very large samples of thousands of objects. These data are coming down the pipeline now. Henrik and I are getting emails constantly of ALMA-GAL data coming in, and obviously we're both reducing it right now because that's what we do. No. Students are hopefully going to help us with that. And I know that ALMA IMF also has they've had some more data coming in for a long time, and they'll have some interesting results. And so when this is happening, we can start to think about doing large statistical studies of the core populations. And I'm really excited about thinking about the core mass functions, which I think are notoriously not great in how they're measured, but I think we can do a better job. And this is something I'd love to talk about in an unconference session at some point. I have a lot of ideas, but no results, so we're not going to talk about it now. But think about that for the next decade. Okay, so on this core scale, these tinier, smaller objects on these smaller scales, I'm not going to cover a lot of that right now. I think a lot of the statistical overview review results are coming in the next 5 years, I would say. But for right now, I can just highlight two quick things. So one is my student, Josh Machado, who's an undergrad at UConn. He's been slaving away with a VLA data set, looking at one of the most massive protoclusters in our galaxy, W51, and measuring the temperatures of all the cores in there, and then doing a core mass function from that, along with ALMA data in the region. And the second thing that I want to highlight is this question of these starless protoclusters. So in our evolutionary scheme, there's a lot of steps missing in here, but the overall picture is that you have something that's starless, and then you go to having stars inside of there. Good? We're not too tired? We don't need coffee yet? We're all on the same page? Okay. So this is, you can argue a lot about what this process looks like in between, what physics is involved, but we know that you have to go from no star formation to star formation being contained in that. And one of the reasons that, the decade of these complete galactic plane surveys was supposed to be so exciting is because it was one of the first times that we were doing these large, complete surveys at long wavelengths. So we were no longer just sensitive to the things that were already forming stars. It was the first time that we were going to be sensitive in a complete way to these starless protoclusters, the things that are still cold and very dense. They're not lighting up in the infrared, but they're lighting up in the millimeter and far infrared. And so I know with the BoloCam team, which is just one of the groups, this is the area that we surveyed with BoloCam. We were really excited about finding some starless protoclusters for the first time. And Brian Swoboda, he worked really hard to identify star formation signatures, and all 8,192 clumps, or however many we had. He did looked at all these different star formation tracers, everything in the literature and everything that was available in existing data, and he identified about 200 starless protoclusters. These are massive, dense clumps that don't have any signs of star formation. Our best candidates for these types of objects here. And here's just two of them. So this is one, this is two, and in vertical columns here is the different wavelengths. And so you can see that at these shorter wavelengths, they're completely dark and show no signs of embedded protostars, but at the longer wavelengths, you can see that there's a massive, dense clump emitting at these longer wavelengths. And so Brian did a follow-up survey of this with ALMA towards 10 of these, and here's those two again. And so you see we have this nice substructure inside of that, but you'll notice that there's actually like a big mess of emission here. These are CO outflows, and so the most starless protoclusters still have star formation happening inside of them, It's just not the high mass star formation that we're detecting with the other surveys. It's this low mass, early star formation, and these stars are probably still accreting. Some of these stars may become the massive stars. And this result, and the result that this happened with the other surveys that were done as well, in addition to some other results here, there's been a lot of evidence that these clusters are continuing to accrete material as they form. So you're not just dealing with this static picture of going from a starless protocluster into going to one of these star forming clusters, but you're continuing to grow material along the way. So if you're looking for the earlier stage, it doesn't look like this. It looks like a bigger cloud that's collapsing, that's accreting material, and basically as soon the stars start to form as you're continuing to collapse the cloud. So it all happens simultaneously, and so the search for starless protoclusters is mostly fruitless, I would say, because they're on larger scales, because you have to look at the dynamics that matters, because it's not a static system. It's something that's changed in the last 5 years, I would say. Okay, so I'm going to now talk about my most fun exception to this rule, which is the starless protoclusters in the center of the galaxy. So these ones actually do hold that they are mostly starless. And so here's one example. Our well-known and much-loved, the brick here. So this is a picture of our galactic center in the 3-color infrared. Here's Sagittarius star, and this is about 100 parsecs on scales here. And now we're going to overlay the longer wavelength data, and you can see that all those cold, dense clouds that were showing up as infrared extinction are now being seen in this longer wavelength emission. And so all this red stuff is your cold, dense gas that might form new stars. So if we look at the brick is extremely cold, very high column density, and about 10 to the 5 solar masses, and yet there's no signs of high mass star formation whatsoever. Dan Walker has a paper he's working on that seems like we do see low mass star formation, but very little, and there's still no high mass star formation. For context, this is like taking all of Orion, which is like 50 parsecs in size, and squishing it down to 3 parsecs, and suddenly you're still not forming any high mass stars, which kind of goes against everything we think we know about star formation in general, and these star formation laws in terms of how star formation behaves with respect to dense gas. So it's not just the brick that's a problem. So we're going to play a fun game. We're going to try to find the galactic center. So here's a map of part of our galaxy in star formation tracers. And I'm going to tell you that the galactic center has 80% of the dense gas in the entire galaxy, and that star formation happens in dense gas. So here's the star formation. Where's the galactic center? Okay, well, I'll give you another hint. So now I'm going to show you a map of the dense gas. Can anyone figure out where the galactic center is now? No? Okay, I thought it was obvious. It's this big thing here. So this is the whole galactic center. So 80% of the dense gas, like it really stands out to me in the second image where you just see a huge area of very dense gas, and that's what the galactic center is. So the central molecular zone of our galaxy, as I said, contains about 80% of the dense gas, but only about 10% of the star formation. Interestingly, it's 10% of the total gas and 10% of the star formation, so as long as star formation doesn't depend on dense gas, you would be fine, but I think most of us are like physics, so therefore that shouldn't happen. It should be denser gas has more correlation. So this is a problem over the entire galactic center. Here's a paper from Jens Kaufmann and some data points from Steve Longmore showing the star formation rate as a function of the massive dense gas, and some other data points from Charlie Latta and Gao and Solomon. And you can see that the CMZ falls below these expectations for the star formation rate by about an order of magnitude. This is some work in prep by my postdoc, Molly Gallagher, who is a PhD student of Adam Leroy in Ohio. And she looked at a bunch of other galaxies and found that the star formation efficiency in dense gas as a function of galaxies that have a bar, that the star formation efficiency also lowered in the centers of all these barred spiral galaxies that she looked at. This is not always the case. In some cases, it's actually the opposite. The star formation efficiency as a function of the dense gas actually increases in the center of the galaxy. But so what we can interpret from that is that galactic centers are weird in terms of their star formation efficiencies with respect to dense gas. This is not to say that star formation doesn't happen in the CMZ. It absolutely does. In fact, some of the most extreme star formation happens there. The most massive stars and clusters in the entire galaxy are there. So if we just zoom in on the central part of our galactic center here, you can see 3 of the most massive clusters in the galaxy, the Arches, Quintuplet, and Young Nuclear Cluster. And interestingly, the Young Nuclear Cluster is actually one of the few regions in the entire universe where I think everybody agrees that the IMF is weird. It's top-heavy. I think there's lots of examples where the IMF might be weird, but I think everyone agrees that this is one case where it's definitely weird. And we would actually love to be able to do this for all the other clusters in the center of the galaxy, but turns out tidal shearing, all of these clusters get stripped apart. And so you could look at the masses of all the stars, but you get completely confused between your field stars and your clustered stars. And so you really can't do an initial mass function at all. So this is one of the reasons why we think that looking at the core mass function, in particular in the galactic center, would be a really interesting way to get at this question, and whether or not this top-heavy IMF is unique to the super weird environment right around the black hole of the Young Nuclear Cluster, or if it's more reminiscent of the entire galactic center. But I digress. Okay. Other things we know about the CMZ, we know that the gas there is very different in many physical properties to the gas in the galactic disk. Any one of these things could affect the star formation. So it's hotter, it's denser, it's more chemically complex, it has higher interstellar radiation fields and cosmic ray ionization rates. And if we just look at the turbulence, this is from Diederik's paper. If you look at the size line width relationship of the CMZ in the dark blue versus high redshift galaxies here, they seem to fall on one relationship, whereas nearby clouds in our galaxy in the green here and nearby disk clouds seem to fall along another relationship here. And so this is just one example of one of the physical properties that's different. That in this case is the turbulence, which is about a factor of 10 higher in the galactic center than the galactic disk. The next thing that we know is that the CMZ is currently underproducing stars by about an order of magnitude. And Ash Barnes had a paper where he looked at every possible tracer star formation rate that we had and found that it was pretty consistent within about a factor of 2. And so it's not like we're missing a bunch of star formation because we just looked at the wrong tracer. Okay, so to address these questions, I think many of you have heard me talk about the CM-Zoom survey before, so I'm going to talk about it fairly quickly, but we embarked on this large survey with the submillimeter array. Yep, and this was a fantastic survey to do with the submillimeter array because you have the combination of a large primary beam, which makes mapping very easy. The galactic center is extremely bright, and so that means that sensitivity is not a major issue. And you have relatively high angular resolution, and we also have a really large continuum backend, so we can do really cool spectral line studies. And so this is the first survey of the CMZ that was able to do high resolution, long wavelength, look at the center of the galaxy and try to figure out what the heck was going on with the star formation there. A large team of people. Raise your hand if you see someone you know in there. Yeah, okay, cool. This is just a picture I like to show, just sort of summarizing the overall, what we did with the survey. So we surveyed the highest column density regions in the galactic center, so about 500 square arc minutes of the galactic center, all the highest column density stuff, so probably where most of the star formation is happening. And so moving on from the brick, because we're so over that, moving on to Bricklet D, which is the new greatest thing. This is the picture that we had before from Spitzer, mostly just a dark smudge with some foreground stars on it. And then with CM Zoom, you can look deep inside of the cloud, see the, ooh, right? See the individual stars that are forming inside of there. So we have a couple of papers that were published already on individual regions and individual objects, and we're working now on doing the overview of all of the survey results. So Perry, who's over here, hi Perry. Perry's doing most of the heavy lifting here with doing a large core catalog, which is hard because I feel like half the time we're just busy having an existential crisis about what a core is in the first place, but you still have to catalog them and come up with their properties. He's done a really good job using this dendrogram algorithm. He's also done synthetic observations, so putting in basically fake sources and then observing them with CASA SimObserve, doing his full dendrogram extraction in the exact same way that he would, and that gives us a really good handle on our completeness. And overall, we're about 90% complete to 25 solar mass cores or 80 solar mass cores, depending on the temperature assumption, which I think means that we're sensitive to most of the high mass star formation, because these are larger scale objects, about 0.1 parsec. So if you're going to form a high mass star in that region, you should have about 80 solar masses total, given star formation efficiencies. Okay, so he's also made these nice mass radius plots to compare with other regions, but one thing you'll notice is that there's really this dichotomy in the population between, I don't know if there's another pointer. You guys can see there's two populations, right? There's one on the top, there's one on the bottom, even if I can't draw it, right? We can all see that. So there's two populations there, and he has a poster where he's going to talk about the origin of those two populations. It turns out it's probably not just a temperature effect, because you'd have to have really crazy temperatures for that to be the case. He also presents some basic physical properties of the cores, and one interesting result, I think, is looking at as a function of column density, just how many individual pixels have SMA sources, and as you go to about 2 times 10 to the 23, you see a strong uptick where basically any pixel in your map that has this column density also has an SMA source associated with it. And I recommend you talk to Perry because there's a lot of nuances in this that I can't present in 1 second. So I'm just going to give some overall view of our overall summary of this because I think I have 2 minutes left. So Dan Walker had a paper where he looked at the detailed study of core properties, and so this was similar to what Perry has done, but just with a couple of sources. And so in the mass radius relationships, he finds that the properties of the cores in the CMZ are extremely similar to the properties of the cores in the disk. So by all the metrics that we could think of testing the cores in the CMZ, they seem really similar to the cores in the disk. They're not higher density or weirder in any way. They seem really similar. Ash Barnes looked at the virial perimeter and the stability of these cores, and he found that they tend to hover around 1 with a large scatter. Those of you who work in galactic disk studies know that this is actually extremely normal. This is sort of what we expect. This is very normal. So again, it seems like these are forming stars as we expect them to form. There's nothing particularly unusual about the properties of the cores. What does seem to be weird is the dense gas fraction, though. And so this is a plot of the overall dense gas fraction of gas in the CMZ measured as a function of just the SMA divided by the Bolocam fluxes, so interferometric versus single dish data. So that's one way of quantifying it, but another way of quantifying it is just if we just look at this map up here, this entire cloud, it's not like we just randomly mapped the CMZ. We chose things that were very, very high column density. So this entire map was extremely high column density, but only a very small fraction of it actually has these compact, dense cores. And shown another way, looking at the probability distribution function, you can see that the entire cloud is above this Lott et al. Critical density threshold for star formation, but only the very tip of the iceberg is actually in compact cores and actually forming stars. So it's not that the cores in the CMZ are different than cores in the disk. It's just that there aren't as many of them as you'd expect for this amount of for the amount of dense gas. And preliminary work has suggested that, so this is borrowed from some work from Jill Rathborn, which I think I forgot to put on the slide, but this is borrowed from some work from Jill Rathborn. The basic idea is that turbulent regulated star formation can explain this, and you would expect that if you have a highly turbulent environment, you'd expect to have one critical density in the disk of the galaxy another critical density in the center of the galaxy based on just the difference in the velocity dispersions alone. And so while this is very far from a definitive explanation for what is definitely happening in the CMZ, it seems like turbulence is a plausible explanation for explaining the lack of star formation. One thing we can say with absolute certainty is that there's no single critical density threshold for star formation, period. If you take one thing away, please, there's no critical density threshold for star formation, and that the star formation rate has to depend on the environment. What we think is happening in our own galactic center is that this is a simulation that Perry is working on, but I'm not talking about it because this is observations. Basically, gas is continuing to flow into the center of the galaxy, and as it's flowing in, it's not reaching this critical density threshold. It takes a while. You start building up the gas. It's still not at the critical density threshold. You keep flowing more material in, and eventually, the gas in the CMZ reaches this critical density threshold. All of a sudden, you have a huge burst of star formation. The whole region explodes, and then you blow out all that gas and dust, and you start the cycle all over again. And so probably what we're seeing is just a low part of the cycle in the CMZ, where the star formation is just exceptionally low. All right, so thank you so much for your attention.
So now we have a bit less than 50 minutes for discussion and questions. Yes, please.
Mm-hmm. The dense gas and also the number of cores depends on the density contrast. Yeah, this will the object looking at
Yep.
the density of the wider environment.
Yeah, that's a great question, Sarah. And so she's asking about the density contrast in these, and we haven't actually looked into the density contrast, but that's a great question. And if you want to join the team and work on that, that'd be great. Otherwise, we'll look into it. But I think that's a great question because the density contrast and the star formation efficiency. Mm-hmm. Yeah. Yep. Yep. Yeah. Exactly, and I think some simulations show that as well. That it's and Perry has some plots that are showing like the overdensity of the region, and that does correlate very strongly with where we see the star formation happening. It's the overdensity that seems to be important. Yeah.
Regarding the low star formation because of turbulence, so the velocity dispersions are high enough to make these structures unbound. Is the explanation? Because basically, in terms of ball density or density, the role of turbulence is to provide these dense structures, and you say you do see the dense structures.
Yep.
So they should be collapsing unless they're unbound because of the velocity dispersion. And you said it's high, but is it high enough?
Yeah. So I think. I read this as like there's a lot about how the process of turbulence affects the process of star formation that has not been well explained. And I feel like it's just kind of right now it's a little bit of a hand-wavy explanation, be like, oh, the simulations show that this might work. But in terms of how that disruption process happens, because clearly there is the turbulence. Turbulence can also trigger star formation in addition to disrupting it. So what is the mechanism that's actually causing the disruption? I think it's a really good question. And so I'd also say that the question of being bound is, I think, again, like talk about existential crises. Like, what does that mean when you have like a dynamic system? Like, are you just drawing some contour around it? And oftentimes, those structures are bound. But if you have like a dynamic system, I think maybe, yeah, I think it's maybe more complex. But I think that the answer is not complete in the literature. So that's why the answer that I'm giving you is not complete. But things that we're interested in, things that we're working on, are trying to understand the origin of that turbulence and the nature of that turbulence, and then in more detail, like how it might actually affect the star formation rates. Yeah.
Yeah, I'll just continue a conversation that we've had in the past
Yep.
on this question. The temperature is, on one slide was 20K,
Mm-hmm.
and on another slide there was a range of temperatures from 20 to 50K.
Yep.
And if you raise the temperature enough, then considering the mass and the gene's mass, there will be a temperature high enough so that even 10 to the 23 will not be enough for a core to be bound.
Yep.
So this continues what Schwell
Yep.
was suggesting. Some combination of turbulence and temperature
Yep.
can raise the threshold for star formation so that even 10 to the 23 is not enough to stay bound for a free fall time.
Yeah, no, that's an excellent point. And so I'm going to, do you have a comment on that, Simon? Okay, so I'm going to turn to Simon in 1 second. But before I do, because I think the theorists are the best people to ask about these questions because I just give the measurements and, you tell me what happens. But one thing I will point out as well is that turbulence is just one culprit that we're investigating, but temperature is possibly another one. I'd also say magnetic fields probably are really important. The only measurements of the magnetic fields are, I think I have, from like Tushar Pillai, suggest something like milligauss magnetic field strengths in these clouds. And that should definitely affect the star formation as well. So I'd say that I want to hear what Simon has to say about the temperature, but it's turbulence is just sort of one culprit that we're investigating. But I think that you make a really good point about the temperature, but also the magnetic fields. Do you want to say something, Simon? Yeah.
So I wanted to point out some work by our former student, Ricardo Franceschi,
Yeah.
So he was doing simulations of dense CMD light clouds in high radiation fields and cosmic ray fluxes with a range of different turbulence energies. And I mean, the results of those are that just the temperature alone is nothing. I mean, if you compare kind of what you get for like the ray field and what you get for the CMD, you do see a bit of fraction star formation. It's not enough of that. So temperature on its own is not enough. Temperature plus turbulence together, it seems to have a much bigger.
Yeah.
What were the temperatures? Well, the ones you expect to find in the CMD environment. I mean, we're looking at radiation fields of 1,000 times growth. And cosmic ray fluxes of similar height. And that gives you dust and gas temperatures which are fairly consistent with what you see in the CMD, and it's not enough because it does raise the gene's mass a bit, but a lot of gas in a
Yeah.
pretty small volume here, so it's really hard to get stuff even above that higher gene's mass.
Yep.
Unless you make things very good.
Yep. Yeah, and
I think
so,
we also
yep.
talked about velocity dispersion turbulence. Isn't there a lot of shear motion going on in the galactic center?
Absolutely. And so I also feel like turbulence is kind of like something that is said without being fully understood. So that's something, Perry is wrestling right now in the simulations. He's trying to decouple like the shear motions from the rotation, from the internal turbulence, but observationally it's even more impossible. Yeah. Okay. Yeah.
Just briefly, yes, there is a lot of shear in this medium, but one of the things is that once those clouds start condensing out of that shearing medium, a lot of the kinetic energy that's deposited by shear through collapse and mixing actually gets converted into turbulent motion. So I don't think it is technically right to say, okay, well, we can really clearly distinguish between shear-driven motion and turbulence. Actually, one usually gets converted into the other. And that is one of the reasons, probably, that this turbulence is so efficiently driven and can be maintained.
Yep. Yep.
Actually, a key ingredient.
And hopefully we can distinguish between like the origin of turbulence by looking at its properties as well. Like, is it shear driven? Is it feedback driven? Is it driven from something else? Yeah.
Right, so in the context of say, the turbulence star formation theories that you showed,
Mhm.
one of the key things is if you drive turbulence solenoidally,
Mhm.
what you say, better out,
Yep.
you end up shaping your density PDF differently.
Exactly.
It's actually much less susceptible to star formation. So
Yep.
rotational modes with kinetic energy are much more important than compressive ones.
Which would be from feedback, yeah. And so this would be right along the lines of what Alyssa was suggesting for a unconference session about using some of these statistical metrics to be able to look at the properties of star formation, comparing with simulations and observations. So like turbustats, stuff like that. Do we have time for Erica? Yeah.
So at high redshift, the gas accretion rates are higher, separation rates are higher, galaxies are smaller, so surface systems are higher. Do you have any expectations, of how the density threshold will change on average?
Yeah, so so actually Diederik's paper that I showed one plot from, the argument in that paper is that the galactic center is a really good analog for some of these high redshift galaxies for the reasons that you mentioned. And so I think that those processes should still be relevant in those cases. But also, I think time averaging might be an issue as well, right? So like in the galactic center, the time scales that people are looking at for these episodicity of the star formation is something like 10 million years or 20 million years or something like that. And so if your star formation tracers are tracing over 100 million years, you might not see the episodic nature. You may just see a flat star formation rate. So I think that but I think that what we're learning about the star formation rate, it has to be relevant. Yeah, you can't have very high densities and very high pressures and have like the exact same star formation as you have in the galactic disk. Yeah. And Diederik could probably say more about that because he studies the high redshift stuff, but maybe not now, maybe later. Yeah. Okay.
Okay. So yeah, if there is no more question, maybe we should move to the last introductory talk of the day. And thanks again, Kara.
Thank you. You don't want this, right?
So yes, maybe the 5 last intervenants of this morning can just line up here. So we're going to try to keep with a 2-minute sharp talks, and I'm going to stand up 15 seconds before. So when you see me stand up, it means that there is only 15 minutes left. And I think we'll start with you. So we first hear Howard Smith.
I get to show my. Hi. So I will talk about galaxy-wide star formation. We've been using 35-band photometry to get the UV to far infrared SEDs from a set of luminous galaxies. So we're interested in the issues of star formation, perhaps due to star bursting or triggered by the AGN. We have re-reduced the data and gotten the photometry from over 250 luminous galaxies, selected mostly because they were all observed with Herschel, so we really wanted to get the long wavelength information. We use the Segal code to extract the key parameters, star formation rate, AGN fraction, dust properties, and so forth. And one of the key goals is to be able to see whether we can interpret high Z objects where we do not have morphology by carefully understanding what's going on in the more local universe. Maybe there's a different IMF going on in some of the most luminous systems, or maybe a different high mass cutoff, or how star bursts work. So we have two key takeaways seen in the plots at the bottom. Basically, the typical plots used for these things is the Schmidt-Kennicott relationship that infers a star formation rate from the infrared luminosity. Now we can measure it more precisely because we fit the full SED. The second one is the main sequence plot that plots the star formation rate versus the mass of the system. Sorry, the focus isn't any better. But the takeaway is that even for our set of luminous galaxies, which are all of the same type, there's a tremendous amount of scatter, factors of 10 to 100, and you cannot assume the star formation rate simply by measuring the infrared luminosity. You cannot assume that a galaxy that's more massive has a bigger star formation rate. There's considerable scatter, and we actually use these data to identify unusual outliers for additional follow-up. Thank you.
Thank you, Howard. Now we're going to hear to Perry Hatchfield.
Hi, everybody. I'm Perry Hatchfield, graduate student at the University of Connecticut, working with Kara Battersby. So a lot of this work is actually already just introduced in Kara's talk. But yeah, so I've been working on building and analyzing this catalog of the CM Zoom large SMA survey of dense clump core-like structures in the CMZ, so in these clouds that seem to have deficient star formation. And in particular, we see that there's I just wanted to highlight a couple results from the catalog that are sort of still coming out, but in particular, we saw this apparent density cutoff where you have SMA cores that are appearing at just about all pixels that have that column density, but you still have a lot of cores that are at lower column densities, which is why we had to use this dendrogram algorithm to pick up things across a wide range of spatial scales and flux scales in the CMZ, because they're all important and interesting. Also, just to follow up a little bit on the two populations in the catalog, it seems largely that population is just due to Sagittarius B2 being this very anomalous star-forming region where you have a massive starburst in the CMZ. And I have some work showing that you can really distinguish it as a completely separate population in terms of its flux and radius properties. And I have some ideas on a poster about why that might be. Also, I've been running these simulations to sort of look at the turbulent properties of the gas relevant to the sort of inflow of gas towards the CMZ, and running zoom-in simulations in a repo based on some of the galactic potential work that was done by Matthias Sormani and that group. So, yeah. Thanks.
So thank you, Perry. And now we're going to hear about the work of Nia Imara, presented by Alisa. Ah, no. Oh, sorry. It's not. Yes?
No, I was going to present my own work.
Yeah, okay. Sorry, I didn't.
Sorry. Hi. So I took Anna's advice to never give a story of your life in 2 minutes. So I'm giving you the story of my life in 10 seconds. Actually, I'm only showing this to you because I was asked to give a talk, a very weird talk a few weeks ago. So I actually have this thing that shows everything that I'm working on and how it's connected. I'm not going to explain that to you. I'm only showing that to you because I just want to show you two little tiny pieces, and I'm going to leave the astronomy-related work to my fabulous colleagues who are here talking about it. And so the two things I want to talk about are this GLUE software program that many of you have heard me say, you should use GLUE, like 1,000 times. And so we're going to have an unconference this afternoon for those of you who actually want to learn how to use that, and I'll show you on the next slide what that actually does. And then I'll just tell you that my other favorite thing here is part of a big project that I've been working on for 5 years that's called Prediction X, which is a history of how humans have predicted their future over the last 4,000 years. And it starts with Mesopotamian sheep entrails and it ends with climate change. But just for fun, I will show you part of it, and I'll put up a poster of this. So this is an interactive that shows you everything Isaac Newton needed to know in order to make a predictive theory of gravity. And if you just click on some particular person, you can go to the part of this big long story that tells you about that person. And so anyway, if you're interested in some fun information visualization and Isaac Newton, I highly recommend that. If you're interested in visualizing your own data, I highly recommend GLUE. And this very quick overview shows you that the three meanings of GLUE are to glue different data sets together so that you don't have to merge them before you start exploring them, to glue different plots together, which is the part that most people know about, and very importantly, to glue different tools together. So one of the things that we're interested in hearing about this afternoon is if you have specific analysis tools or environments that you want to connect to GLUE. We've done that for things like Worldwide Telescope already, but we'd love to do it for your tool too. Thanks.
So thank you, Alisa. Now we're going to hear Mo Chixian. Sorry.
Hello everyone, my name I'm Xixian Mo. I'm from Nanjing University, and I will introduce my work on on the observations towards the high-mass star-forming region areas 18330, and we firstly obtained the orientation of magnetic field from the polarization angle of dust emission, and then use the DCF method to estimate the strength of the magnetic field. And we get the large scale of the field by fitting an hourglass model, and then derive the dispersion of the field angle. And then I get the velocity dispersion from VLA's ammonia 1 lines data and the volume density from the dust continuum emission. So it gives us the estimated magnetic field strength about 7.5 milligauss, which is strong. But an interesting thing is the excess of the outflow, and it's almost perpendicular to the orientation of the magnetic field. And why some surveys and simulations predict that the strong magnetic field could align with the outflow, and because of the magnetic braking. And so we are still waiting for a higher resolution data to figure out what happened in this area. If you are interested in my work, we can talk about it later. That's all. Thank you.
Thank you. And the last talk is Sandro Techala. Sorry.
Okay, good morning, everyone. So I'm working on galaxies, in particular on the scale between like dark matter halos and galaxies, and now slowly getting also more interested into smaller scales within galaxies and how star formation is sustained. It's quite interesting because galaxies can be actually understood with very simple equations. So, for example, you can write down stuff like here, that the star formation rate is related to the dark matter accretion rate, and you can explain how the cosmic star formation rate density as a function of redshift evolves over redshift. And also, when you look at the given epoch, you can find these quite tight relations between the star formation rate of a galaxy and the total stellar mass. And these things can be quite well understood with these very simple approaches. But of course, as we have heard, there is, star formation is much more complicated. And so how is, this kind of simple picture related to space resolved scales? And I've looked into some cosmological zoom-in simulations. And what we find is that galaxies actually not are staying stationary, on these relations. They actually evolve up and down. And so they oscillate about this kind of, star formation equilibrium with cosmic time while they build up their stellar mass. And the interesting part is that the spatial distribution of star formation within galaxies, so the buildup of bulges in galaxies, is related to these galaxies oscillations. And so at the moment, I'm very interested in understanding these up and downs in star formation with cosmic time, and how this is related to the burstyness in star formation. And so with Nevin Chapler, we have introduced this framework of basically understanding these bursts of star formation with the power spectrum density. So basically understanding this as a stochastic process. So this borrows a lot of ideas from the HN light curve community. And what we were doing is applied this framework to redshift 0 galaxies, Milky Way mass galaxies, and we find that the star formation actually decorrelates roughly on the dynamical timescale. So the galaxy loses its memory of previous star formation events when you wait for like 200 to 400 million years. And at the moment, I'm thinking of this framework and apply it more to actually, the framework of GMCs, because I believe if we would be able to measure, these bursts as a function of time for an ensemble of galaxies, we will be learning something of, how GMCs and the GM life cycle is sustained in galaxies. So thank you very much for your time.
So thank you, Sandro. So I think now we're going to move to the next same place as yesterday for the unconference session, and we're going to have coffee there, I think.
We could also, for just a couple minutes, put up more unconference ideas. We can transfer them over there. Do we? Yeah. Do it when they get there. You should write down. Okay. You don't want people to get here. Okay. So.